right, so last but certainly not least, we're happy to have Jonathan Ju, who will be speaking about widths, minimal submanifolds, and symplectic embeddings.
Well, thanks, Dan. It's good to be back in whatever sense. So knowing that it's the last talk, or perhaps vibing that this might happen, I thought we would do sort of a more casual talk, or in any case, it's a talk in a couple of parts that may or may not mix together. Just sort of a few things I've been thinking about that are loosely connected. And the starting point is some symplectic geometry, which really arose out of a question so a couple of friends that I knew in grad school asked me while I was in grad school down the road, and then we sort of brought Antoine in. And so part of what I'm going to talk about is joint with them. And of course, if we had a robot hand at the CMSA, maybe Antoine can raise it to correct me whenever I do anything wrong. But yeah, I thought we'd just sort of have a sort of nice discussion. Okay, but in any case, disclaimer is, of course, I am not a symplectic geometer by trade, but I think probably most in the audience are also not super experts in symplectic geometry, so that's where I want to start. So a symplectic manifold. Okay, that's just an even dimensional smooth manifold with a particular two form. And the symplectic condition is that it's closed and non-degenerate. Okay, so that's all the symplectic manifold is. And the canonical symplectic manifold is just R2n, but I'm going to write that as just Rn cross n, just to be super clear. So it has coordinates P and Q. And the standard symplectic form, let's write this, omega standard, is just where I wedge the conjugate variables together. So it's dp1 wedge dq1 plus all these guys, wedge dpn, plus dpn wedge dqn. Okay, and so this is not just the canonical guy, this is really the local picture as well. And this is the Darboux presentation. So locally, you look like Rn with this particular form, and it'll be useful to just sort of talk about a little bit of extra structure that the canonical example has. Okay, so the extra structure I want to talk about comes from realizing that, okay, it's even dimensional R2n, we can identify with Cn. Okay, so we get a complex structure, or really slightly more generally an almost complex structure. So we'll call that J. Okay, and the point is it doesn't just have the structure. The structure is, of course, compatible with the structure we had before, right? Sorry, let me call this J standard as well. And so a complex structure is compatible, so the condition is, well, let's take my two form, I'm going to test it out on, sorry, I hope everyone can see that. So two vector fields, x and y, but I'm going to stick we stick a J in there, and that turns the skew form into a symmetric form, and the compatibility is that the symmetric form is positive definite. Cool. Okay, so that's an extremely quick introduction to the basic category that we're working with. And
why are you calling J standard though?
I just mean the standard complex structure on CN. So it's the one coming.
You're talking pretty above.
Yeah, for this one. So yeah, maybe I should say. Okay, so one of the key questions is to understand exactly how this category works, right? So we'll pose it as a rigidity question of maps in this category, right? So I guess you always just take the word and call it a morphism. So we want to understand, when you can have a symplectomorphism, and that just means a map which preserves the symplectic form. Okay, so there's one easy invariant. And again, so some of this story will be reviewed for some people, but I think it always helps. So one easy invariant is, well, if you preserve omega, then you preserve, of course, the nth wedge power of omega. Okay, but the nth wedge power is just up to a constant. It's just the volume form. Okay, so in particular, any symplectomorphism has to be volume preserving. And so now the next question is, is that the best you can do? Right, so if n equals 1, right, if we're in the simplest case, then it's literally, I mean, you've done nothing, right? You haven't taken any wedge powers, so it really is just area preserving in dimension 2. But in higher dimensions, then you start to ask, well, maybe volume preserving is not the only thing you have to preserve. Okay, so the sort of famous example now is the Gromov non-squeezing theorem. Okay, so colorfully referred to as the symplectic camel. And the problem you ask is, well, if I take, let's say, a ball of radius r, right, so just a Euclidean ball of radius r, and so.
When you say easy invariant, do you mean I mean, are you talking about the volume form locally, or are you talking about the interval of volume?
Just the form. Let's say the form. Yeah. Okay, but if I take, so the non-squeezing problem is I want to fit a camel through the eye of the needle, and so I'm taking a big ball, that's my camel, and I want to ask, can I shove this into a cylinder? So that's for us going to be a 2 ball of radius 1 cross a bunch of linear factors. Right, and so I want to ask, can I embed these via a symplectomorphism? Okay, and so the famous result of Gromov is that you can't do it, right? So if the radius is too big, then you can't shove it into the cylinder and be a symplectomorphism. Right? So we can write it this way. So if you can embed it, then the radius has to be small enough that you can actually fit it through. Okay, so hopefully it's clear that this is somehow in between, right? So you definitely can't fit the ball, a big ball into a small cylinder with an isometry, but you could do it with just a locally volume preserving map, because you could just squish it down and make it long enough to keep the volume the same, but otherwise still shove it into the cylinder. Okay.
Is it so special about 2 ball? What about 4?
Yeah, that's not clear to me. But well, I guess so. I mean, 2 dimensions is somehow special with the 2 form, right? Okay.
No, I'm saying if you want to say B4 was R2n minus 4.
So that's smaller is what? Like a polyball.
Okay, this is different.
Okay. Yeah. No, again, we're going for a last day talk. It's all a discussion, right? Okay. So the problem that was that happened upon me, but that we were interested in, is okay. You've got this great non-squeezing theorem, but how can we quantify this guy? Right? So you know that it doesn't fit, but is there a way to quantify this theorem? And it's an open-ended question in a couple of ways, as we'll see. But the direction we took is you know that you can't fit into this cylinder, right? So whatever you're doing, some part of the ball has to escape, right? Or on the other side, right? That means that somehow that's maybe the portion that you couldn't get into the cylinder, right? That you couldn't fit. And so we have this dual question of how much has to escape the cylinder, or conversely, right, how much you have to delete before you can fit it into the cylinder. So we refine this question to how much do we have to delete so the ball of a big radius take a bad set. Right, so after taking away the set, then it actually does embed into this guy, B2. What? Okay. Cool. And again, this still leaves something open, right? Because there's a question of how to understand this term, how much, right? So again, what do we actually quantify it with? And something that's maybe a little surprising is that volume is not a good measure of how much you have to delete. Let me say 2n differential volume. Maybe giving away some of my cards, but and in some sense, maybe this isn't so surprising because we already know that volume preserving, right? Just dealing with the volume isn't really the most natural thing to do. But in any case, there is a theorem of Kartok which makes this concrete. So the theorem says that given any compact set in R2n, then I can find a symplectic map from R2n to itself. Let's call it phi. And so the property of this map is that if I look at the image of this compact set, right, so I've shoved it in, and I want to measure what escapes the cylinder. Right. So I'm exactly looking at the part that escapes. This thing has volume as small as we like. Okay, so I should have said for any epsilon. Okay, so the escape volume can be as small as we want. So volume is not really a great abstraction for what's going on. Okay. Cool.
Is the proof effective? You actually, in the case of a ball with the wrong radius, you see what it does?
Yeah, okay, so
just like one like spike or is it many spikes?
Okay, so this was my plan. My plan was to sketch, to sort of invert the usual talk structure and give you a sketch of a proof of Gromov non-squeezing and then avoid having to deal with the technicalities of our actual proof. So let's move on to that, actually. Maybe I want to keep the statement up, so we'll mess with this board. Okay, so let's spend some time discussing the proof of non-squeezing. Okay, so suppose we can do it, right? So suppose we have a ball, and let me just take B4 for simplicity. So B4 of radius r, and we do this in the paper, so it'll save us some thinking in a moment. But let me just toss a factor in there. If you're paying attention, what I'm measuring instead of the radius, what I'm writing down instead of the radius is like the two-dimensional width of this guy. But you should think of this as, it's radius r. It really is radius r. So let's suppose this does embed into the 2 ball of radius 1 crossed with R2. Okay, so for technical reasons, it's nice to just work with a compact space. Okay, and again, in 2 dimensions, the only constraint is the area constraint. And so I can just compactify the ball into a sphere as long as the 2 sphere has just a little bit more area than the ball. Okay, so I can shove this into S2 with area A as long as A is greater than pi. And my guy here is essentially compact, so whatever I end up into, I can just take the quotient by a large enough k, right? I can fit it into a big enough torus. So there's a map down here. Yes, that's right. Yeah, so again, just area preserving is enough. Area form preserving. Okay. Okay, so by this little fait accompli, I can think about a symplectic embedding into S2A cross T2 instead. Okay, and the point of doing this, one point of doing this is that this guy has a natural complex structure. Okay, so the complex structure on T2 is clear. That's just the standard one on Euclidean space. This one is, well, okay, S2 is really CP1. And so there's this complex structure coming from CP1. And then I just take the sum of those. Which n? Sorry. No, sorry. So this one works for any n. But the original manifold is even dimensional.
Yeah, it'll be 2.
Oh, no, but this S2.
Two maps to S2.
Oh, it's always B2. Oh, sorry, yeah.
Yes. All good? Yeah, it's the last step. Okay, so there's this complex structure, and there's also a nice foliation that goes with this complex structure, right? So there's a foliation by holomorphic curves. So we can draw this like this. So we'll draw S2 on there, and then the bottom is the T2. And so I'm just thinking about the vertical foliation by 2 spheres, right, by holomorphic curves. Okay, good. So the point is, each slice here is holomorphic and has area equal to A. Right, it is just a copy of S2A. Okay, but now we have our, we also have our ball, that's B4R. And so this is mapping in to some region. So that's the image of phi. Okay, and there's also a natural structure on the image, right? Because I can just take whatever I had here, the standard guy, and push it into the image. Right, so this is no problem. So on here, I have the push forward. Okay, and what we want to do is we want to interpolate outside this between the push forward on the image and the guy that we started with, right, the one outside. So J1 is some interpolation again between J0, right, and the push forward. Okay, and the sort of key point here, which I'm not going to talk about, but this is like where sort of all the machinery, all the analysis, all the hard yards are actually done, is in Gromov compactness. And the upshot really is that you can deform one to the other. So you can, I can take J0 and deform it to give me J1, again, through almost complex structures. And essentially there's a matching foliation that goes along with it, right, as I deform this. Okay. So what does this mean? This means that, well, I'm not going to have the red foliation anymore by the time I deform to J1, right? So I've changed it. I've changed the structure on the inside. But sort of outside, well, maybe up to a little neighborhood, right? So if I'm really far from the image, then I do just get, right, the complex structure hasn't changed. My foliation is still by those S2As. But on the inside, I get something, right? I get something, something different. And for anyone, just a disclaimer again, I'm being extremely loose with technical details, like what I mean by a foliation. Okay. But this is the spirit. So yeah, the new foliation is going to look like this. And the point of this new foliation is that these are now, so each slice is J1 holomorphic. And the symplectic area only is a homological invariant, right? So the point is that because I still have those S2A slices, the area of these slices is still equal to A, right? Okay, but now I can again pull back this foliation to the ball. Okay, so now on the ball picture, well, I pulled back the push forward of the standard guy. So what I'm getting here is each slice is really holomorphic, and the area, well, I'm only going to pick up a piece of that slice. So the best I can say is it's area at most A, but that's fine. Right? That'll turn out to be fine. Okay. And if everyone's happy with that ball picture, I'll just remove this board. Okay, so again, there are lots and lots of certainly sufficient minimal surfaces experts here to see how to finish the proof. So to finish the proof, well,
So the J1 you said is between J standard and this new graph.
yeah, so it should be equal to the push forward inside, and then maybe you give yourself some room, and then it should be like far enough away, it should be equal to the old one. Okay. So if you grant me this foliation with its properties, well, so one way to finish the proof is there exists a slice that passes through the origin. And, okay, it's holomorphic, so in particular it's minimal. Okay, but the area of a minimal surface that goes through the center of the ball is at least the area of the equatorial disk. Bigger than pi big R squared. And again, just to be sure, this is by the, for example, by the classical monotonicity for minimal surfaces. Okay, but we said the slice is supposed to have area less than A, yeah? Okay. And A was really anything bigger than the disk of radius 1. So straight away you know that the radius has to be less than 1. Okay. Cool. So I hope that's clear. Yeah. Okay, so I wanted to mention, so that's certainly one way to finish the proof. And the feature is that it uses a special slice, right? So you know that you have all these minimal slices, and then you take one that you know passes through the origin and has large area. Okay.
This constant is less than the one in those of shot.
So I mean, if the radius is less than 1, you just slide it in. I mean, just translate it into the cylinder. It already fits in the cylinder if R is there.
So one in shot.
Yep. Yeah, sure. Okay.
The way you presented it, is that going on proof?
I think this is something resembling the original proof. I should say, I learned this from 18904 back when I was an undergrad from MIT, and then promptly forgot it, and then relearnt it on this project. Okay, but there are other ways. There's at least one other way to finish the proof. And so this is sort of the idea of a width or a waist inequality. And I'm not going to be super precise about the difference. But so there's this theorem of Gromov where if you take, you have to bear with me for the statement a little bit. So we'll take a continuous map from the sphere to n minus k dimensional space. And really what I want to think about are the fibers of this map, right? So I'm imagining this as really a parametrization, right, of a family of k cycles. Okay, the point is that, well, the width of the sphere is given by equators. And so that's what well, you would imagine that the width of the sphere is given by equators, and that's what the theorem says. So if you have such a map, then there exists a y in the parameter space, meaning, okay, you have some special fiber. And if you look at if you measure this fiber, it beats the measure of the equator, right, the equatorial SK of the sphere. So it beats the equatorial SK. Yeah. Okay, and a feature of this theorem is actually that you get substantially more, but so I'll write it just for completeness, that you also get an estimate, so not just for the area of the fiber, but also for any t neighborhood of the fiber. Okay, so the t neighborhood of this special fiber beats the t neighborhood of the equatorial SK as well. I think actually you can put the quantifier here. Okay, so what this is saying is as long as I have a foliation by these guys, then there is a fiber which may or may not be minimal, may or may not go through 0, right? But the size of that fiber should beat what's expected. Okay. Okay, so hopefully from that bit of discussion, it's clear that we could finish the proof as well if we knew the same theorem, but with these s's replaced by b's. Right, so this is a theorem in the sphere, and so what we really need is this follow-up by Akopian and Karasev, which says that we can replace Sn and Sk here respectively with Bn and Bk. Okay, so that will really say that in the ball, as long as I have a regular enough family of k-cycles, there's one special guy that has large enough area. Okay, and again, maybe just to be super clear, this one holds for any t, but this one, the reduction, only holds in the limiting case, right? Meaning genuinely for the area of the fiber, not the neighborhood anymore. Okay. So I had a couple of more comments on the width, but maybe I don't want to keep everyone waiting. If you notice that, sorry. Yeah, sorry, let me write this out. So what you want to compare the fiber to is, again, an equator, right? So that's all I meant. So the equatorial SK, and again, the T neighborhood. Right, so in a ball, you don't have an equatorial sphere, you have an equatorial BK, right? Okay, so that's all that's happening. Okay, so again, you can see this is one way to finish the proof. Again, not using the fact that you have a foliation by minimal guides, but just basically any foliation at all. But also when you... Okay.
What is this proof involved and that?
Yeah, so it's pretty ingenious. I won't say I understand it fully, but there's like an upgraded Borsuk ulim that goes into it. So yeah, for this one. So to get from here to here, it's a reduction using actually my favorite map, which I love to teach in calculus, which is like if you take a two-sphere, right, and look at the cylinder of the same height, then the projection away from the central axis is an equal area projection. Okay, so what this achieves is like a projection from a sphere to a ball of one dimension lower, but this is actually enough for you to deduce one from the other. Yeah, and so actually in the paper they call this the Archimedes map, and so there's a citation that says like Archimedes of Syracuse in like 200 BC or something. I really hope to include one of these at some point. Okay, but so I have more to say about the widths, but I thought I should sort of close off the first part, which again is how to quantify this theorem, right? So I wanted to look at B4 with this large radius, and I want to delete a set right? And I want to ask, how big does that set have to be for me to actually successfully embed this guy into the cylinder? Okay, but you sort of start to piece together with all these T neighborhoods. I mean, this is essentially what you're gonna do. You're gonna play off this big fiber against the area bound you have from the foliation, and so the result, again, this is with Kevin Sackel, Antoine Song, Umut Varol, Gunesh, and Vassal. Okay, so the result is that the right thing to look at is, again, the limit as t goes to 0. And that's really the Minkowski content, which we weren't quite able to show something sharp for, but we were able to at least bound the Minkowski dimension in a sharp way. So if we can embed this guy into the cylinder and the radius is big, then the Minkowski dimension of the deleted set has to be at least 2. So that's how we decided to quantify this. And again, the proof is essentially playing off this sort of waste inequality with the area estimate from the foliation, plus you need this classical Heinz-Karcher estimate to understand the volume of a tube around a minimal submanifold. So that's essentially what's going on. Okay. So sorry, just if anyone's not familiar with the Minkowski dimension, it says exactly sort of what you want it to say. So the Minkowski dimension says essentially the T neighborhood, if you measure its volume, should be like, so it should be like T to the ambient dimension, right? If it were a smooth submanifold, it would be the ambient dimension minus the dimension of the submanifold. So Minkowski dimension D really means this sort of behavior. And again, not getting technical about lower or upper or all of these things. But it behaves like at least a 2-dimensional set. Okay, and we have a partial converse as well. So conversely, so the 4-ball of radius root 2 take a Lagrangian plane, successfully embeds into the cylinder of radius 1. And this plane is in some sense surprisingly simple. So this one is just Q1 is Q2 is 0. So I should say maybe after we posted up the paper, I think a couple of Swiss mathematicians contacted us and said, actually, you can do some symplectic shenanigans and embed a bigger ball minus a 2-dimensional set into the cylinder as well, but they can't do it for every R, so it's still not a full converse. And of course, that's one of the questions that maybe I should pose. Okay. How are we doing on time?
Good. Yes.
Oh, okay. We have several pictures of what, of how you would construct something, but somehow whatever we do doesn't really beat it or doesn't give us a clue for what more to do. It's a
Symplectomorphism on the entire ball, but only that plane takes out.
no, I want to say it's only defined on.
It's only defined on
Yeah.
that subset, so this is not like this leaking out concept.
No, so so what I missed
This
is
is the leaking, the deleting.
this is the deleting question, and so we also looked at the other question, which is almost the same in a different way. No, it blows up at L, yeah, if I remember right. Okay, well, yeah, I mean, if anyone else has any questions, this is sort of part 1 I had in mind to give you this sort of result using widths or minimal surfaces. And well, then the part one is also sort of a pretext to start talking about these width or waist inequalities. So there's some interesting things. So maybe one thing I can mention is, okay, so again, there's this, there's a reduction to the ball. There is also, so Gromov also has a waist inequality for Euclidean space with the Gaussian measure. Okay, so what he does is you can replace Sn by Rn with gamma, where this is the Gaussian, just a rotationally symmetric Gaussian. And the same inequality holds, right? So you should replace the volume with the Gaussian volume. But it also works for T neighborhoods. Okay, so there's a Gaussian waist inequality. And then there's sort of very interesting theorem of, sorry, so again, the waist inequality tells you that there's one special fiber, right? But there's an interesting theorem of Klartag where, again, we're looking at essentially Euclidean space. Except I put Cn, so I really want to look at Euclidean space with the Gaussian measure, except now it's complex, and so what's coming is I'm going to ask for more regularity on the map, right? So it's not just continuous, now the whole map is holomorphic. And so this is actually more information, I think, than what we had in the non-squeezing, right? So not just every slice is holomorphic, but the whole map. So if the whole map is holomorphic, then, in fact, for every t and y, we have this fiber estimate. Okay, so the Gaussian measure of the t neighborhood of the fiber, so it beats the Gaussian measure of the t neighborhood of a Euclidean subspace. And let me just write the condition first. So this is so E is a C n minus k subspace such that the distance to the origin, right, the distance from the subspace to the origin is equal to the distance to the origin of the fiber. Okay, so this maybe looks a little funky until you draw a picture. So let me give you one related theorem and then the picture, okay? So this is, well, sorry. Oh, sorry, CK. Thanks, Christos. Yeah, actually, let me draw the picture first. So the picture is, I have my space, I have my origin. Okay, now I have some fiber, and I have some fiber. Maybe that point of closest approach is y. Okay, so the best thing should be the subspace with that same distance, right? So through y, but orthogonal to the origin. That should be the best subspace in my mind. Okay. And so again, this is a result for all t, right? So it bounds also the neighborhood, but you could consider the t goes to 0 limit. And again, that really just measures the area of the fiber compared to the area of this orthogonal disk to y. And in that case, it actually follows from this estimate of Brendel and Hung, and it only uses the minimality. So this one follows from this theorem of Brendel and Hung. So it says that if sigma k in the ball is minimal, and so the area estimate we saw before is that if it goes through the origin, then just the regular old monotonicity formula tells you that you beat the k-disk through the origin. But if instead this thing contains y, then the area of sigma k beats the area of the bk orthogonal to y. Okay, so exactly this one. Okay, so this was a theorem. This was something I think from 2016. And so sorry, I should say you can deduce this one basically just by integrating it up on larger and larger balls. So this was about 2016, and the method is just a first variation argument. So it's really, you just have to be smart enough to come up with this vector field, which they obviously are, and you plug it into the first variation, and almost straight away it tells you the estimate you want. And okay, maybe okay, it's the last talk. We can be a little loose. So the shameless self-promotion is that back in the day, I showed that this also comes from some sort of monotonicity. I won't write that statement down, but yeah, so I've been thinking about this since I was a student here, and just recently, I think it's probably safe to say it, but maybe I won't. Well, definitely I won't tell you a proof. But so sort of work in progress with Keaton, who failed because he knows what I'm going to say. So the work in progress is that you can generalize this. So instead of taking the Euclidean ball here, you can prove essentially the totally analogous estimate for balls in a space form. So the same estimate, so the analogous statement. So the ambient ball, instead of being a Euclidean ball, we can do essentially any hyperbolic ball. And okay, so we can do some balls in the hemisphere, but we can't so far get every ball. So depending both on k. So if you're in a space form, you need to also say the radius because they're not equivalent anymore under scaling. So it depends on k, r, and the position of y. So we don't have a great tight result in the sphere, but we think we can do it for any hyperbolic ball. Cool.
K being
K is the dimension of the minimal submanifold. Yeah. And again, it's a case of coming up with a clever vector field, which should not be interpreted as a claim that we're cleverer than they are. Okay. Well, maybe there's, I have a few minutes, so maybe there's one other story I can mention, which is that, again, we had this sort of width-waist inequality. So what we said is essentially this Gromov inequality. So that essentially says that the k-dimensional width of the n-sphere is realized by the equatorial SK. And but for this statement, you don't need to prove it using this like complicated, this very clever upgraded Borsuk-Ulam, right? So this one you can do with min-max theory, because you know that the width is going to be realized by some stationary, so really minimal submanifold, but okay, maybe you worry about the regularity. It should be a stationary varifold. Okay, but I mean, you know that the area of any minimal submanifold beats the area of the equatorial SK, so just under the minimal assumption, you know this. And so this gives you an estimate for the width. Right. Okay, on the other hand, we could also finish the problem. This other one, the Sokopian-Karasev, really said that the width of the ball, right, should be equal to the area of the K-disk, right? And I mean, this really also comes from a similar estimate, right? So it's still realized by a minimal submanifold. But, well, sorry, it's still realized by a stationary manifold. But stationary now, the ball has some boundaries, so it's stationary with respect to variations that also fix the boundary of the ball. And so this is really a free boundary minimal surface. Right, so okay, and so in the ball, if you want to finish it this way by the min-max approach, what you need is an estimate for the area of any free boundary minimal surface in the ball. And so this is another theorem of Brendel, is that such a sigma k is bigger than the area of dk. I wrote a little note on this recently where, you know, technically if you look at it, Brendel just writes it for smooth guides. And again, from the min-max theory, unless you have a nice regularity theory, like in codimension 1 and low dimension, I think Shin and Martin did that. Unless you have a nice regularity theory, you really need the estimate to work for varifolds as well. So that was something we also checked. Okay, so maybe that's enough stories. I hope this was a fun discussion.